virtual reality, video games, scientific simulations. In making realistic dynamic visuals for people all across media, physically accurate collision detection and solution is super important. I first got interested in this stuff when I watched the Sebastian Lake video where he tries to simulate a Lagrangian fluid. I thought, let me try that. And then I realized I don't even know the first thing about simulating particle-particle interactions, let alone a massive project like that. So that kicked off an investigation of mine into collision simulations, which is the premise of the next couple videos on this channel. Huge shout out to the Reducible YouTube channel who made this incredible video on building collision simulations, which guided my exploration of this intimidatingly fast field. Before we get into the video, if you're new here, my name's Jagat or Jugs, and I learned how to build stuff on here. Right now I'm mainly focused on computational physics stuff, but when I get back to campus in the fall, I'm going to try experiment with some mechatronics and machine learning projects, so stay tuned for that. I just started this channel a month ago, so if you'd like and subscribe, that helps a ton, but without further ado, let's get into it. Let's start off with a basic example. We have this particle in a box. In this model, we assume that the particle has negligible mass in comparison to the box. It starts off in the center, shot out at some velocity, and carries on until it passes through the box. Let's fix this. First, we have to code the detection of the collision, which is relatively straightforward. We define the left, right, top, and bottom of the box. Whenever the position of the particle plus its radius crosses the boundary of a box, there should be some change in its velocity. But in what way? Intuitively, we would assume it to bounce off the wall, which indicates the velocity would have flipped depending on which wall it's hitting. For instance, for the top or bottom, the velocity's y component would flip, whereas for the left to right, the velocity's x component would flip. Let's see if the physics checks out. Here's our situation. Say there's a detection of a collision at the right side of the box. The particle is traveling with some 2D velocity vp, while the box is still, or has a velocity of 0. The impact force on the particle when the particle hits the wall acts at a right angle to the wall, so it's completely horizontal and to the left. While the impact force on the wall is just the opposite of this due to Newton's third law. So we know that whatever happens, the change in velocity for either will happen in the x direction. We can also make the assumption that all collisions in the system are elastic, which means that momentum and energy are conserved. We can then use the principle that momentum in the x direction is conserved to write that the initial momentum, which comprises of the initial momentum of the particle in the x direction, and we can set that equal to the final momentum of the system in the x direction, which is mvp x prime. Sorry, this shouldn't be prime, plus mvbx prime, where vbx is the final velocity of the box in the x direction, and big M is the mass of the box. So we can rearrange this to first find the velocity of the box post-collision to get mvbx prime equals mvpx minus mvpx prime, and then vbx prime is just equal to m over m. If we then factor this out, you get minus vpx prime. So we made the assumption that the mass of the particle in comparison to the mass of the box is negligible. So that's basically the same thing as saying if we take the limit as m over m approaches 0, m over m, vpx minus vpx prime, and we're taking the limit of this quantity to 0, so this whole expression just becomes 0. So now that we've found that the x velocity of the box post-collision is 0, we now can see that the momentum vector of the box is also 0 because it's just m times v. So the final x velocity of the particle must be exactly opposite its original x velocity for the net change in momentum to be 0. Because if we find that this vector was 0, which we did, this vector has to completely cancel out the original vector. So that confirms our intuitive assumption. Whenever a collision is detected at either our left or right boundaries, we flip the x component of our particle's velocity and send it on its way. And for our top and bottom boundaries, we just flip the y component of our particle's velocity. But for further precaution, I found that it works better to simply just specify the sign of the velocity post-collision to prevent the particle from possibly getting stuck in the wall and continuously flipping back and forth between negative and positive, and that just causes problems sometimes. So specifying the sign of the velocity I found was the safest way to go about this. So this all seems well and good until we try and speed up the particles. Let's see what happens. As you can see, as the particle hits each wall of the box, it appears to go past it a significant amount before ricocheting back. This phenomenon is actually a really common one in computer graphics and is known as tunneling. The higher the speed, the uglier this gets. In trying to see how to deal with this problem, I discovered the concept of continuous collision detection. I'll only be trying to implement a very basic version of it since it is quite a loaded topic, but in essence, it involves continuously predicting when collisions will happen and routing a particle based on its expected trajectory following a collision within a frame before it happens. So this is in contrast to what we're doing right now, which detects collisions discretely, meaning that on the frame itself we are resolving the collision if we detect that the particle is currently beyond the wall. In predicting when a collision is going to happen, we start off with this simple equation. X at time t of the particle is equal to mt plus x at time 0. So this is a simple y equals mx plus b style equation where we just have our dependent variable bx and our independent variable bt. Let's say that the frame that we're currently on is given by t equals 0 and the next frame is given by t equals 1. We can then calculate the slope of this x of t equation by doing delta x over delta t, where we get x at t equals 1 minus x at t equals 0 over 1, which is the number of frames between those measurements, and that just gives us x of 1 minus x of 0. So if we plug the expression that we got for the value of m into our original equation, we get x of t is equal to t times x of 1 plus 1 minus t times x at time equals 0. And this is a pretty classic linear interpolation equation. And we can pretty easily derive the same for the equation for y of t. So if you wanted to calculate when a collision is going to happen on either the left or right boundary, you would solve for t sub c, where t sub c is the time at which this collision is going to happen. And we can also consider that for the right boundary at least, x at this time that the collision is going to happen is equal to the boundary, so the right boundary is x position, minus the radius of the particle, because the x displacement of the particle is measured by where the center of the particle is. So if we solve for t sub c for the left and right boundaries, which is using the x linear interpolation equation, we can also do the same for the top and bottom boundaries where we're considering the y linear interpolation equation. The question is now, how do I implement that in code? And it turns out to be pretty simple actually. First, we find the current coordinate x0, y0 of the particle and what the coordinate will be in the next frame, which is x1, y1. We then calculate what time from now in frames that will reach each of the boundaries of the box using the equations that we just found. Then we check if any of those TC values is less than 1 frame. And if it is, we immediately route it to the position it will be at TC. We do this by taking advantage of the coordinate of the box's boundaries and the linear interpolation equations where we can predict the values of x and y at a given time t. Alright, now after implementing the continuous collision detection code, we see that the collisions with the walls look a lot cleaner and that there's no longer noticeable tunneling. Now the screen recording looks a little whack, but that's just because of the frame rate of the screen recording. On my end, trust that it looks absolutely fine. What if we want to add more particles in the mix? In most applications, that's almost always going to be the case, where you have multiple objects that you want to be able to detect and solve collisions for, especially for simulating a Lagrangian fluid, which was my motivation behind delving into collision simulations in the first place. The physics behind this gets a little more complicated and was a little trippy for me to understand at first, but it's pretty cool, so bear with me. It's also important to note before getting into this derivation, dealing with circular particles makes things a lot easier. In fact, a common simplification of more complex shapes is to try best approximate it with a circular hitbox. The first step in simulating particle-particle collisions is to first be able to detect when they actually happen. And this turns out to be pretty simple. It happens when the distance between two particle centers is less than or equal to the sum of their radii. Now onto the actual collision solution. Let's start by considering the one-dimensional case. From the law of conservation of momentum, we equate initial momentum to final momentum by stating that m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Since we assume elastic collisions, we can also say that 1/2 m1v1 squared plus 1/2 m2v2 squared is equal to 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared. Through some pretty ugly algebra, we find these two equations for the respective final velocities of the particles, v1 prime and v2 prime. These equations will be useful later. Now let's define a normal axis and a tangent axis, where the normal axis connects the centers of the two particles and the tangent axis is tangent to both the particles. We can define a unit normal vector n hat by normalizing the vector that connects the two particle centers, and we can define a unit tangent vector as negative n hat x, since the normal and tangent axes are perpendicular. Then we can get the velocity of each particle as normal and tangential components by projecting the two velocities onto the unit normal and the unit tangent vectors. The next step is to find the new tangential velocities after the collision. When two particles collide, the contact force is actually fully in the normal direction, so there's no acceleration in the tangential direction. Therefore, the final tangential velocities are no different to the initial tangential velocities. Finding the final normal velocities turns out to be a straightforward process because of our derivation of the final velocity equations for the one-dimensional case. We're allowed to use this equation because we're finding the velocity change in solely this axis, which means it's one dimension. Lastly, let's convert our final normal velocities and final tangential velocities back into vectors by multiplying them by their corresponding unit vector. Our final velocity vectors for either of our particles is just the sum of their normal tangential velocity components. There are a couple adjustments that I found to be helpful in preventing two particles getting stuck inside one another, which happens more often with higher velocity particles. This problem is rooted in the particles continuing to overlap even after the velocity is updated and there's been a frame since. One way to deal with it is to calculate what the overlap is, which is the difference between the sum of the particles' radii and what the actual distance between the particles' centers is, and separating the particles along the normal axis accordingly. An additional measure I took, which turned out to help, is to correct any potential computational errors that would cause the overlap to still persist by gradually separating the particles until any remaining overlap was fully gone. And here we have our simulation of two particles in action. Now there's one last problem that I thought was pretty funny and kept running into, and it's that one particle could just randomly tunnel through the box. That shows the importance of continuous collision detection, which would help a ton here, but is a little complicated for particle-particle interactions. Instead, we can just stick with our discrete approach and add this function which somewhat hackily fixes our problems. So far, we've covered collisions of a particle with the box's boundaries, an improved way of detecting collisions of a particle with the box boundaries, and a model of particle-particle interactions. We've largely gone into collision solution, but there's more to be discussed on the detection side. See, if we increase the number of particles, the simplest approach of detecting collisions could turn out to be the most computationally expensive. Many call this the naive approach, where we simply come up with all the pairs of particles and check each pair for a collision. But logically, doesn't it make sense not to check for the collision particle on one side of the box to one that's on the other side? What about a pair of particles that clearly have no overlap on any axis with one another? To what extent can we rule out possible collisions that are improbable? Catch all of them in the next video where we'll delve into some interesting collision detection algorithms. Thank you guys so much for watching. Feel free to leave a comment below. I'll be reading and responding to every single one, so whether it's feedback, it's a question, literally anything, don't be shy to hit me. So yeah, see you guys in the next one.